Thanks very much for inviting me here. I'd like to give you an overview of the problems that the petroleum industry is facing. And I won't go into great depth on any one particular problem, but the oil industry has a lot of uncertainty in it. And the kinds of tools that they need may not require, supreme accuracy. A lot of the time we're working at depth where we actually don't know the material properties even. And so I'd like to give you a brief overview of the kind of tools that the oil industry is looking for. And the areas for simulation that they already use are reservoir simulation. So that's typically for well design and operations. So what rates do you pump, etc. They'd like to optimize the value of their reservoirs. And offshore structures, there's the design of those. They have issues with rogue waves, etc. There have been some, disasters like BP offshore. They're developing Pore scale, what they call digital rock, that laboratory experiments are quite difficult to do and are very expensive. And if you can come up with a simulator that can give good predictions, then that would be of great benefit to them. One of the biggest areas of interest is in hydrofracture of shales. It's revolutionized the amount of oil and gas that we've got available. Literally, it saved the US. And even with the price of oil down, still hydrofracking is a big issue. And we understand very little about it, especially in complex rocks like shales that are very inhomogeneous. And also then on the downstream side, reactors for the cracking of petroleum products. And so we've been developing a number of methods at MIT. SPH is one of them, and I'll focus a little bit on SPH applied to the coupling of solids, fluids, and fracturing. And I'll end with the multi-physics problems that obviously we'd like to go all the way from nanoscale up to macro, but there are great challenges in doing that. We've been focusing, and I think there's Chris Leonardi been talking about, for example, particle suspensions in fracture. So these are proppants that hold the fractures open. It's no good in hydrofracking unless you can hold the fracture open. So if you just hydrofrack, open up a fracture, it'll close under the in-situ stress, and you'd get no benefit from it. So you try and prop it open with particles. Usually they're sand, but ceramics are used these days. These give rise to non-Newtonian fluids, very and quite complex behavior. I think any tools that you develop today are going to be applied in 3D. You're going to have a lot of unknowns. So typically now you're dealing with millions of unknowns in 3D. We're developing for Shell, they're aiming for 1 billion. Aramco have, when they do oil reservoir simulation, run with up to 3 billion unknowns. So you're definitely writing parallel codes these days. And that's very painful if you have to do MPI and things like that yourself. And so you'd like to have some tools for developing these codes. So this is typically what the oil companies, the questions that they have in reservoir management, that they've got operational uncertainty, geologic uncertainty. You don't know what the material properties are typically, and you'd like to have a business plan for operating that field that is profitable. So I'll just give you a quick review, for example, of the problem with reservoir modeling. So typically you've already got some history of operating these reservoirs. Let's take Saudi Arabia, where they've got, a 20-year history in some reservoirs. So the first thing you have to do is to try and match the history, and you don't know the material properties. You've got a few boreholes there, you've got some seismic, but you really don't know the material properties, in this case, the permeabilities. And so you're trying to adjust these permeabilities in your model, and you've got, literally millions of cells, and you'd like to match these flow rates. And it's a non-unique problem that you can match those flow rates with, many sets of models. So typically, they're trying to run literally tens of thousands of models. And for example, Schlumberger was saying they're running like 60,000 variations on a model with different material properties to see which one matches. And so you'd like to have a better way or faster way of doing this. If you run a full order model, the FOM is full order model, ROM is reduced order model. So you'd like to, if possible, run with a reduced order model that still maintains the accuracy. And so there's been quite a bit of research. This is some research of one of my PhD students. And they've been reducing, for example, 4,000 state variables down to 180. And the kinds of results, this is a full order model on the left, and then a full order model with run 50 times, with a reduced order model run 150 times. And you get very good results, typically within 5%, something like that. You can actually control the accuracy. And so this mixture of running reduced order models with full order models is very profitable. So what we're trying to do is to develop a geomechanics platform. So this is a parallel platform where we can plug in various codes. So for example, SPH, finite element, discrete element, lattice Boltzmann. And to do that, you need to be able to have a library of some kind that will, for example, take arrays and distribute them across machines. But also on a single machine these days, you've got maybe 36 cores. And those cores, you need to optimize those. So you've got two levels of optimization, one on the cores and one across machines. And you'd like a library that automatically does this for you. Very few people want a program with MPI. That it's a brutal level of programming. So we've got a library that allows a programmer not to worry at all about the parallel side. I mean, they have to be aware that it's parallel, but writing the code on top, for example, an SPH simulator, takes about a month rather than a year. So you can reduce the time these days. Writing these codes doesn't take that much time. Testing them and validating them does. You're still going to take an awful long time on that. So let me just talk about SPH and why we chose SPH. So smooth particle hydrodynamics evolved in the astrophysics area, actually, and it's basically a partition of unity. And so it's not really a particle method in the sense of a molecular dynamics or discrete element. What it is that we have a region around a point in space that has an interpolation kernel, and that we're interpolating a function with these displaced kernels. Yeah? So they should at least represent unity. If we can't represent unity, then it's not going to be much good. But we can do this, and by plugging in this expansion into our partial differential equations, we're actually solving continuum problems, but using particle methods, if you like. So often they're drawn, these regions around a point are drawn as spheres, but they're not really. Mathematically, this is a continuum method. Now, because we're dealing with these points and these particles, if you like, we can do things like add forces in between them. But it's still a continuum method. So that's the main point to realize about SPH, is that although it may look like particles, they're not. So typically it's order H accurate and order H squared, ensuring that order H, we don't get order H squared, but those are the terms we're neglecting. So this is what a particle method often is drawn like. So this would be for a fluid. Now, the nice thing about this is you don't have to put particles where there is no fluid. So you get free surface for nothing, basically. And one of the other things to notice is that these can shear over each other very easily. Later we'll see when we come to fracture, it's very easy to fracture in mode 1 in tensile, but it's not so easy to shear, mode 2. That's a very tough one. If you try to do it with finite elements, you run into horrendous problems. So any kind of sharp-pointed method, if you like, is going to have problems with fracturing. So this was first applied in the area of fluids. So there's variations of SPH. There's the classical SPH, Greengold and Moynihan, and they used a stabilized version of this. There's something called corrected SPH, Liu and Bonnet in Swansea. And that should be not XFEM, that should be XSPH, a stabilized method by averaging the velocities. And then there's a stress point SPH that basically, which looks like very much like a finite element where we have nodes that have velocities or displacements, and then we evaluate the stress at a Gauss point. Now, the difficulty with all of these is that these points can move. And so it's quite difficult to keep the accuracy that you get with a nice layout of these points. So often in test problems, we can just lay the points out in, say, a cubic array. But it's very difficult once, especially in fluids, once things start moving, to keep that order. So you apply the continuity equation, energy conservation, etc., and the constitutive equation can be either so this is basically equation of state, this is what decides whether it's a fluid or a solid. So it's a very nice method in the sense that we can address fluids and solids in the same program. There's absolutely no problem with doing that. So the tensile instability is often an issue, but there's a recent paper, and these people have done a lot of great work in addressing this tensile instability. So this is basically where things are regions under tension, particles can tend to clump together. So you need to do something to stabilize that. And there's a recent paper, I'm going to jump over these equations actually, XSPH. But there's a great paper that's just come out by Dess and Cleary, which evaluates the classical SPH. So going back, so there's been 10 years, 15 years of work in adding things to the SPH that actually slow the method down. We have to do these extra calculations. So Cleary's looked at uniaxial compression and compared it with finite element. And his conclusions are basically that it compares very well with finite element. Finite element itself has problems that, and in some cases, SPH is superior to finite elements. So that's read that paper. If you want to read any paper, it's this paper by Dess and Cleary that I'd say would give you a good overview of that. So I'll talk a little bit now about applying SPH to pore scale modeling. So in this, you need to be able to do multi-phase fluids. You need to be able to handle, say, oil, water, and gas. Typically, when they're running reservoir models, they're running 9 phases to 11 phases of fluids. So this is a typical test problem where you're pushing fluid through a packed cell where you've got narrow pore throats and then quite large pore volumes. So this is quite a good test problem. So there's a semi-analytic solution by Larson and Higdon, and then these are SPH results. And this is going up to solid volume fractions of 90%. We've actually run it up to 95% solids. So it gets more and more difficult as we overlap these spheres, and the pore throats get narrower and narrower. Because we've got to use more particles. We have to have at least, say, 9 or 10 particles across a pore throat, and then you have a massive volume inside the pore that will burn up hundreds of thousands of SPH particles. And then we did some blind tests for Schlumberger and got reasonable results. These were the results with the green triangles by David Holmes, that's now a professor in Australia. So let me just show you. So the problem typically is that you get very different results whether the rock is wetting or non-wetting. So on the left here you've got fingering. On the right, the water clings to the rock. So it's quite critical, and with oil, you're trying to drive the oil out. So if you get fingering, the red is the oil here. So if you get fingering, you get what they call water cut. So you're injecting water in one well to push the oil and produce it in a second well. And what you don't want is for the water to go all the way through like fingering, because you're not pushing much oil. So you want something more like on the right than on the left. This is work done for Shell on rogue wave impact on structures. So here's a wave tank, and so that's a solid body in there. And the nice thing is we can generate waves that are very difficult to generate in a real wave tank. So, for example, we can focus a wave at a specific point quite easily. And this was against some laboratory tests where you have a slug of water and a steel column, that you get the first hit on the front face, and then you get a second hit on the back face. But these are the experimental data is the black dots, and then the various XPH. We're using extended XPH here, and we get good results for those. So we spent about a year validating SPH for Shell. So we're collaborating with them. They're updating the code now to be able to import CAD models. So you'd like to be able to pull in full CAD models. This is work. This is SPH with some better rendering. So there'll be a big wave coming in from the right-hand side in a moment. But most of the fluids that you see from Hollywood, for example, or in adverts, are done with SPH, just with good quality rendering. So this is some work done in University of Freiburg by Gisem McKinsey that then came to MIT as a postdoc. And what she's doing here is adding in foam particles to make it look good. It's no more accurate than the other ones, but it just looks a lot better. But it's quite good. And this was done by her husband, Nadir Kinsey, and this is multi-phase flow. And this is a tough problem. So if you try this with, say, finite elements or finite volume, these interfaces are quite difficult to capture. So this is quite a difficult one to do. And the balls are basically different densities, and there's one stuck down at the bottom here. So let me just briefly talk about the oil shale problem. So these are very tight rocks. Typically, permeabilities are down at 10 to the minus 20, 10 to the minus 21. Very, very tight, but difficult to get out. So nothing's going to come out unless you fracture it. And these are the wells in Canada. Just to show you the number of wells, we've got data in the US for 20,000 wells. There's something like 40,000 up there. But literally, there's a blizzard of wells. Now, when they do these hydrofracks, they don't measure anything. It's costly to measure. So typically, you've got data from one well out of maybe 5,000, something like that. So you've got very little data, yet you're spending maybe 20 million to frack a well. And so the fracking, typically wells are horizontal these days, that you'll try and follow the geologic structure. Often they're cased, so then you have to fire a charge through the casing to make hydraulic contact with the rock. So this is showing the perforations, and then you're going to seal off part of this and then pressure it and inject water and then particles. Now, this hydrofracking takes about 4 hours. It's not a dynamic process. These are not dynamic fracks. So you can imagine the rock is under in situ stress, and now I inject fluid at more than that in situ stress. So let's say this is 20 megapascals. I've got to inject maybe at 21, something like that. And these are just drawings of what they think the fracks look like. Now, you've got to, as I say, inject as well proppant into those. So you've got to inject these sand particles, if you like, or ceramics. The way that you frack, typically they'll frack from the end of the horizontal. So this line here is the horizontal well, and then this would be the first frack. Now, by fracking, you've increased the stress state. So the second frack may not propagate as well. Yeah, so this is called stress shadowing. So they're looking for strategies for fracking. There's no reason why we should frack in this order. And there may be better orders to frack in. The US shales vary quite greatly in whether they're brittle or whether they're ductile. This was a test we just did by injecting foam into a container. Sorry, I've got 5 minutes to go. Good. Okay. And this is what you'd call a really good frack. That's pretty amazing. So you just inject it. It was under no stress. And this was at about 10 degrees centigrade. Same material, now you get a mess, basically. This would be no good as a frack. Now, this is what's happening in some of the shales. In some of the shales, they can't frack them. They're not getting this nice plane to run. So they want to understand this behavior. There's some theoretical penny-shaped crack models that I think have got serious flaws that are not very realistic. Typically, the conditions ahead of a frack are that we've got a pore pressure pulse. We've got issues with the flow of this material. It's a gel-like material. It's not water. It's more gel-like. So it may not actually get to the tip of the frack, depending what the frack is like. So you don't know exactly what the pressure conditions are along that frack. And then finally, you'd like to put the particles in there and have those move. So we looked at all the methods around for fracturing, handling fracture and flow. And these are some results from a finite element. This is Los Alamos. So there's a few kind of competing codes out there. Now, the problem with the finite element with tetrahedra is you're going to get a surface like something like that. And now you've got to shear it. And now you've got a geometric problem. Basically, you've got a problem of tetrahedra intersecting tetrahedra. And that's a very difficult problem to solve. So from time step to time step, for example, I'll suddenly, on one time step, these two tips of the tetrahedra are not interacting. Next time step, they're inside each other. Now the question is, which face did they go through? Where do I put the force? The other problem I've got is the normals at these tips are non-unique. I don't know what direction these forces are in. So there's a horrendous geometric problem with finite elements, with pointed elements, if you like. What you'd like are smooth potentials, where you know the normals and you can shear things. And that was the great attraction for SPH, because they shear very easily over each other. So I'll just show you. This is SPH for plasticity. And we compared with the Brazil test. I'm going to go fairly quickly. Oops, let me just see if I can get that video to play. So a Brazil test, so these are the stresses plotted on the right on the vertical from the top to the bottom. So at the top platen and the bottom platen are the left and the right, okay? And then what happens is, in the middle, you get a tensile stress. Now, depending on your slip conditions on your platens, you'll get different results. And typically in lab tests, they don't know what those slip conditions are exactly. So you'll get a dead region, if you like, a little triangular region. Often, if there's no slip on those platens, there can be, so at the top and the bottom near the platen there, you'll get a little triangle where there's almost no stress horizontally. Then in the middle, there is stress. So what will happen in some of these tests is if you have no slip, you'll have a fracture that runs vertically but doesn't reach the ends, doesn't go right through the specimen, it'll stop. Whereas if the ends slip, it'll just split the specimen totally. So these are different results for different end conditions. And we get very good agreement with the elastic model. This is SPH. And I talk to the lab people, and sometimes they do even get little particles in the middle. We happen to get this little particle in the middle there. So again, we'll often, with metals, use an associative flow rule, and you'd get fracturing something like this. And non-associative, you'll get a totally different fracture pattern. Now, for rocks, we're going to have to get lab tests done to tell us what the properties of these rocks are. So that's about where we are. This is blast loading, which is coupling a gas with a solid. And the final one I'll show you, this is with an in situ fracture already in place, and I'm done. Let's see if it'll run. Sorry. Yeah. So we're fairly confident that we can couple solids and fluids, and by fluids I mean gases or for explosives as well. So SPH is a very robust method. It has some issues, but in general, sorry, I'll just go back one there. It gives you tremendous flexibility in handling different material properties. I'll stop. Thanks very much indeed.